Five? I'm
So-
not bragging about this right now.
Today we're gonna go over Chem 118A final review session. I think today we're gonna get started with like summary of reactions that you can use for synthesis
Okay.
problems, such as the organo
So then go back
Metallic.
to the Wi-Fi.
reactions, right?
UCD gas.
Redox
Open browser and connect.
of alcohols,
Log in with existing
epoxide,
account.
ring opening. Right, let's do SN2, D2, SN1, D1. Let's say alcohol plus HX reactions, alcohol plus H2SO4 heat reactions, alcohol to, let's say, the good leaving group, like chlorine, bromine, iodine, which are going to be the SN2 like reactions,
Oh.
right? Like the PBr3, SOCO2, PI5. So right now I'm just listing a list of reactions that are very common for synthesis ones for 118A. There's also, you could see epoxidation with MCPBA, right? With MCPBA. Now, for Levens, she also does ring opening with unstable rings like cyclopropane, cyclobutane, with hydrogenation like H2PDC, right? Ring opening. And the very first reaction that you guys learned in OChem, which is halogenation, right? With X2 and light. Ring opening, halogenation. Right, with X2 and light. Do you guys think, can you guys think of any other reactions that are used for synthesis?
Ether?
Ether. Yep, epoxidation, epoxide ring opening is here. Ether reactions like cleavage with HX, that's more for predicted product.
Okay.
I don't really see that for synthesis ones because it gets messy.
Okay,
But you
that's
can
right.
definitely do ether cleavage as well.
Yeah, Williamson.
Yes, Williamson ether synthesis, yeah. Yeah, Williamson. Syn. Ether. Synthesis. Right? And there is an intermolecular and intramolecular one. This can also make an epoxide. Right, the 3-membered ring. Let's see, what else?
Oxidation.
Oxidation, yeah. Oxidation and reduction of alcohols.
Oh, redox. Yeah.
Yeah, redox. Like, and those will be using reducing agents and oxidizing agents. And there's like a weak and strong ones as well. So those would be good. Organometallics. Okay, so this will be a good list to start with right now. Which ones are you guys confused with the most to prioritize here?
Epoxide?
Epoxides? Let's do epoxides. So we're gonna do epoxide ring opening.
Intermolecular one, Williamson.
Yeah, intermolecular and intramolecular Williamson ether synthesis. Okay. Now let's do that. I'm going to erase this word and go over epoxides. Okay. And then at the end, I'll give you guys practice synthesis problems using like all of these reactions right here. Okay.
I'm just writing down things I need to review.
You writing down everything then?
Now, when we talk about epoxides, we first have to talk about ethers. Right. And the ether functional group is going to be an ROR, right? And the R's could be any hydrocarbon chain, like a methyl, ethyl, isopropyl, tert-butyl group like that. Right? An ether, epoxide, is going to be a 3-membered ring where oxygen is one of the atoms of the 3-membered ring. there is 2 carbon atoms here, 1 oxygen atom right there. So this right here is an epoxide. Right. Now, to form epoxides, we could do something called Williamson ether synthesis. Okay. And Williamson ether synthesis would be 2 reactions. The first reaction is going to be an acid-base reaction. The second reaction is going to be an SN2 reaction. Okay? And the starting molecule for Williamson ether synthesis is going to be an alcohol, which I'm going to abbreviate as ROH, right? And then we're going to get into an ether, which is ROR. Okay. Now, there's intermolecular and intramolecular Williamson ether synthesis. So let me talk about intermolecular. Here, where the nucleophile and electrophile are going to be on separate molecules. So I'm going to give you a simple example here. Let's say we have this alcohol reacting with these reagents here. First step, NaH. Second step, some random primary halocane, like that, right? Whenever you guys see sodium and A, what charge is that associated with?
That's fine.
Yep. This hydrogen here would be a negative charge, which is a hydride ion. The sodium here is positively charged, which is a spectral ion. We could just ignore that. That's not going to interfere with the reaction. So this hydride ion right here is a strong base. Right. And this strong base here is going to look for the most acidic proton. And we see here the most acidic proton here is going to be this hydrogen directly attached to the oxygen. Right? Because it has a partial positive charge since it is attached to this electronegative oxygen atom like that. Yep.
Is there any way you could use NaOH?
NaOH would be a weaker base, so we wouldn't be able to deprotonate this alcohol.
So it wouldn't make a 100% oxide ion.
Yeah, it would make a 100% alkoxide ion.
So if you ever want to take that H off, NaH is your best bet.
Yeah, NaH would be your best bet to take this alcohol H off. Right. So I'm just gonna draw out the bond explicitly between the O and H to show the mechanism here clearly. Right. This hydride ion here, H minus, will be the base to grab this proton. The bond between the proton and oxygen is gonna go onto the oxygen like that, and that's gonna give you an alkoxide ion. Right. Where the oxygen has a negative charge because this oxygen here gained a pair of electrons from this bond. Now this alkoxide ion is a nucleophile because it's negatively charged. When we bring in the second reagent, which is this halocane right here, we see that this is going to be the electrophile because it's partial positively charged, and this right here is going to be the good leaving group. Right. So the way that I'm going to do this here is that I'm going to star my nucleophilic atom, which is this oxygen right there, and dot my electrophilic atom, which is that carbon there. This nucleophile here is going to use one of its pairs of electrons to attack this electrophilic carbon to make a new bond between the star and dot, between this nucleophilic oxygen atom and positively charged carbon atom right there. We're going to have to break off and kick off the good leaving group there to conserve the octet rule. Now this here can be tricky, but the answer here would be this, where this is the oxygen right there that attacked this red dot carbon, right? Where this is the new bond that is formed between the nucleophilic oxygen atom and electrophilic carbon atom like that. And we see that this red dot carbon here, which is this red dot carbon, has an isopropyl group attached to it. So I just copy and paste that over to the side as the decoration. The Br is gone, it floats out as Br minus, giving us an ether here, ROR. So this is Williamson ether synthesis because we started with an alcohol and then we ended with an ether in 2 steps, 2 reactions. First step was an acid-base reaction where we deprotonated the alcohol to get the alkoxide ion, and then second step was SN2 where we used the alkoxide ion as a nucleophile to attack a primary substrate, haloalkane, to get our ether right there. Right. This is different than the usual SN2 reactions that you've been seeing because the nucleophile that you're used to seeing is NaCN, NaN3, neutral amine, but this can also be a nucleophile to attack a primary substrate like that. Right. Okay. Now here's question for you guys. Let's say we have the same alkoxide ion, but this time I reacted with this haloalkane here. What would the reaction be?
We're gonna get E2.
E2, right? Because this carbon here is secondary attached to the good leaving group. This OR minus here, right? OR minus is a strong base, strong nucleophile. Base, strong nucleophile. So if you look at that chart, or if you want to understand it, this strong base, strong nucleophile is going to look for an acidic proton, right? And this right here is going to be the alpha carbon attached to the good leaving group, and these right here are the beta carbons. And because they're both equally substituted, it doesn't matter which proton we grab. This base is going to grab the beta proton, make a double bond here, and kick out the good leaving group right there to create this E2 product here. And then ethanol would be formed, like that. So when you do Williamson ether synthesis here, you have to use a primary substrate to do SN2 reaction. If you do a secondary substrate, SN2 wouldn't happen, E2 would happen, because this substrate, this reactant here is a strong base, strong nucleophile. Right. Any questions on the intermolecular mechanism before I move on to the intramolecular mechanism? Okay. Now, I'm gonna erase this and go over intramolecular now. And this is also recorded and will be posted as well, so you guys can watch it over again. But it doesn't get to it doesn't get down here to the recording, so let's get. Let's see, okay. Any questions? Okay. Let me do intramolecular now. Okay. Okay. Now for intra molecular Williamson ether synthesis, that means the nucleophile and electrophile are on the same molecule. Right? And all intermolecular reactions, it doesn't have to be Williamson ether synthesis. It could be intermolecular, like other reaction. Then all of them would form rings, right? Form rings. Okay. So let's say, for example, we have this structure. And then we react it with NaH. Right? We said that when you see NaH, we think of a hydride ion because the Na here is a spectated ion with a positive charge, making this hydrogen a negative charge. So this spectated ion here would be ignored. This hydride ion we said earlier was a strong base, strong nucleophile. So it's gonna deprotonate this alcohol to give us this alkoxide ion here. Now, we don't see any second step of haloalkane or a substrate, so we can bring in another molecule as an electrophile for this nucleophile to attack, right? But we do see an electrophile somewhere in this molecule, some positively charged atom, which is going to be this carbon right here that's directly attached to this good leaving group, bromine. Right, so this O minus here is going to go around, attack that carbon, pick out the good leaving group. And that's gonna make a new bond between this oxygen atom and this dot carbon here, wrapping around and closing a ring. And the way that I like to number it is I like to number 1 my nucleophilic atom, and then I go all the way
Hey, you might
until.
want to scoot your board back a little bit, just because I think it's kind of hard to see back here. Yeah,
Yep, better.
that's probably better.
Okay. A 6-membered ring like here, where number 1 is the nucleophile, number 6 is the electrophile. Right? Everything else is decoration. We see a methyl group here, ethyl group here, and isopropyl group there, which we would just copy and paste on carbons 2, 3, and 4. But before we do that, I'm going to draw out the template of this product, which will look like this. Right? Where this is our 6-membered ring. Oxygen is part of the ring because that's our number 1 atom. So I could number this like 1, 2, 3, 4, 5, 6. Oxygen was our nucleophile, aka the star that I labeled. 6 was our electrophile, aka the dot. This is the new bond right here that we formed between the nucleophile and the electrophile. That bond between 1 and 6 was not there before. But that bond was created when we did the attack, the intramolecular attack right here. Okay. Now everything else is copy and paste. We see at carbon 2, there's a methyl group. At carbon 3, there's an ethyl group. And at carbon 4, there's an isopropyl group. Okay. And this is a cyclic ether right here. Cyclic ether. Right. And because this is like 6-membered ring, we can call this an oxocyclohexane. Okay. Any questions on this mechanism here? Yeah.
In any case of when you're numbering it on the ring, it doesn't matter if you go counterclock because it's going to be.
Right. So in this case, I went counterclockwise, but you could have numbered it this way, clockwise.
Does that work for like any type of when you form any ring?
Yeah, it would work for any type of intramolecular reaction. You can number it however way you want, in however direction. The most important thing here is make sure like the groups attached to the carbon that you numbered is consistent. Yeah, like if you numbered it this way, the methyl group would have been here, ethyl group would have been here, and isopropyl would have been on the same carbon still. Yeah.
And
Yeah.
so if you had like an alkene,
Yeah.
anywhere in that, does that now can you not make a or alkene or alkyne? Can you not make a ring anymore?
Oh, so if there is an alkene between let's say 3 and 4,
Yeah.
right? The base would not affect that because alkene is also a base, which is the first thing in 118B. It would still be putting its alcohol, which is a sulfoxide ion, and it will still attack, and there will still be double bond between 3 and 4.
Okay.
Yeah, so there can be alkene right there. Yeah.
What if it was? You have it in your mouth. What if you had it between 2 and 3?
Between 2 and 3, yeah, it'll still be an alkene right there.
Okay, so it wouldn't affect it.
Yeah, it wouldn't affect it. But if there was acid, right, instead of a base, like H2SO4, H3O+,
Yeah.
the alkene would be destroyed by acid.
Oh yeah.
Yeah,
Okay,
yeah,
that makes sense.
yeah.
And, then, and you can do this for any chain of carbons, right? Like
Any chain of carbons, yeah. It could even be 3-membered
Oh, wow,
carbons,
okay.
even though it's like unstable, like you learned about ring
Yeah.
strain. We can still do 3-membered rings, which would lead us to the epoxide.
Because
that
it's
one
just
is there.
stronger. Is that why?
Because it's a strong nucleophile,
Okay.
angry reactive nucleophile. Yeah. Yeah.
If there's multiple leaving groups, should we consider which one's the best?
Yeah.
As our only product, or
If there's multiple good leaving groups, like let's say bromine here and chlorine here, then you choose the best leaving group, which would be bromine. But let's say there was a bromine here at this position. I'm gonna draw it out. Like let's say we have something like this. Which one is the better leaving group here? Oh wait, actually, that would not. Let me make this clear. Which one is the better leaving group here? Bromine or chlorine?
Bromine?
Yeah, bromine is the better leaving group because it's a bigger atom size. The negative charge is more polarized. It could breathe more. There's more breathing for the negative charge. But if we use bromine as the leaving group, that would make a 3-membered ring. If we used this as the leaving group, that would make a 6-membered ring. Which ring is more stable? The 6-membered ring. So we would actually prioritize this good leaving group instead over the bromine. Even though this is the worst leaving group, this would end up with a more stable ring product molecule. Okay. Yeah. Okay. Good. Nice. Yeah.
So what if like on the bromo, like on your original molecule,
Yeah.
instead of it being primary, it was like secondary or tertiary? Would you not be able to create a ring anymore?
Oh, like if it was
Would there be like any steric hindrance?
Oh no, you don't have to work by steric hindrance for epoxide ring opening for this reaction here. Yeah. Like if there was like another group here, you can still close the ring for epoxide like that.
So do we always react with the leaving group that's farthest away? Or
The one that would make the most stable ring, because if there was another leaving group that was like 10 carbons away from here,
it's still 6?
it would still attack this 6-membered ring because the 6-membered ring is the most stable ring, right? Stereochemistry, when we attack, that is good. It would invert stereochemistry because this is SN2 type reaction, and it goes through a backside attack and inverts stereochemistry. So if this bromine was a dash, and we attack the carbon, kick out the bromine, the new bond would be a wedge, inverted, right? And vice versa, which is good for synthesis problems, the stereochemistry. Okay, so this is SN2 back side attack. Inversion. Inversion is stereochemistry, like that. Like wedge to dash or dash to wedge for the leaving group. Okay. Any other questions on this intermolecular Williamson ether synthesis? Skip. Now, I'm gonna actually give you guys an example of one that would create this epoxide with stereochemistry. Here. And then after that, once we get to epoxide, I'll go through opening up the epoxide in acidic conditions versus basic conditions. So let's say we have something like this, NaH. What do you guys think is going to happen between this molecule and this reagent here?
The acid-base reaction?
Acid-base reaction, where the H- or the hydride ion is going to deprotonate this acidic proton and create this alkoxide ion, which is the strong nucleophile, strong base. This is intramolecular because we see the nucleophile, which is this oxygen with the negative charge, is on the same molecule as this electrophile, the partial positive charge carbon here attached to this good leaving group. So when we come in to attack that carbon there and kick out the ring, we see that we're going to form a 3-membered ring. And because we said this is a backside attack SN2, this dash bond here is going to invert into a wedge bond, like this. Right. And this is our epoxide right here. And I can also star it like this. This is the starred atom. This is the dot atom. This right here is the Niels bond that we formed between the star and dot atom. And the way that I numbered it, 1, 2, 3, is this 1, 2, 3 atom like that. And that is epoxide, which you can open it up in acidic conditions or basic conditions. Yeah.
Let's say the bromo was on a wedge. Can you just rotate the bond to make it a dash, and then, or can you not do a backside attack?
Oh, like if the bromine was a wedge.
And then so you can do backside. Can you flip the bond?
Yeah.
Or rotate?
Yeah, you can rotate the bond. Like if it was something like this right here, and the bromine was a wedge bromine, we do not want to form this epoxide. This is going to be unstable, where like one bond is wedge, one bond is dash, because like it's kind of weird. Like this bond is going like out of the board into you guys. This bond is going into the board away from you guys, so it's gonna be very weird. So we don't want to. We want to avoid this right here, right? We want both bonds to be both wedge or both dash, and to do that, we see that this is a single bond here, which can do free rotation and rotate into this position here, where I'm gonna keep everything here the same with the alkoxide ion. I'm gonna swap these two places, right? Where the methyl is now down here, the bromine is gonna be over here now. But when I do that, this wedge here is gonna become a dash, and then we can do the same reaction here to get this epoxide right here. Which is different than this epoxide because like we see that this is kind of like a cis-like structure where the two R groups are facing in the same direction compared to this epoxide right there. Yeah, that's a good question. Because you'll see some problems where you need to rotate single bonds sometimes.
So wait, we need to make it so the OH and the halogen are facing away from each other?
The OH and halogen are anti to each other. Yeah. And that would allow us to make an epoxide where both bonds of the epoxide are facing in the same direction.
Okay.
Right, because if the halogen and O minus are facing in the same direction, that would form an like unstable epoxide structure. So we could rotate the single bond right there. Okay. Now we're gonna do epoxide ring opening and acidic versus basic conditions. Now, epoxide opening. I'm gonna look at basic conditions first because that's the shorter, easier one to talk about. So when you think of basic conditions, you think of negative charges, like either fully negative charge or partial negative charge. And some examples of this would be like hydroxide ion, alkoxide ion, and those are the main ones that you'll see. But you can even see Grignard reagents. Right. Because this carbon here, directly attached to the magnesium, is negatively charged, and that is a strong base. Strong nucleophile. So when you say Grignard reagent, that is going to be in basic conditions. And the basic conditions would have all SN2 properties. Would the nucleophile in SN2 attack the more or less subside?
Less.
Less subside, right? Because we want to avoid steric hindrance for SN2. So, attack less sub-carbon to avoid steric hindrance. And it will also have the same stereochemistry as SN2. What happens to the stereochemistry in SN2?
It inverts.
It inverts, yeah. Inverts through backside attack. So, an example of that would be something like this. This is an epoxide right here. And we see that these two carbons of the epoxide are partial positively charged because they're attached to this electronegative oxygen atom. So they're both electrophiles here, right? When you look at the reagent here, sodium, like we said, is positively charged, making whatever is attached to it negatively charged. This is just a solvent, a product solvent. We can ignore that. That's not going to interfere with the reaction. The thing that's going to react though is the alkoxide ion, methoxide here, right? Because it's more reactive, less stable. So let's say this is carbon A and carbon B. Which carbon would be attacked by this methoxide ion here if it's SN2? Like A, right? Because it's less substituted. So we're gonna attack A right there, making a new bond between this oxygen atom and carbon A. When we do that, we have to conserve the octet rule and kick off this bond onto the oxygen right there. So the 2 electrons in this bond here are gonna go onto the oxygen right there. And we're gonna do a backside attack, so this wedge bond, right, is gonna like become the new dash bond. Well, like this wedge bond isn't gonna become the dash bond, this wedge bond is gonna go onto the oxygen, giving a pair of electrons, but this pair of electrons right here, which attacks this carbon, will become the dash bond, right? Which is gonna be like this, O, H3, and then this wedge bond here stays the same because nothing touched that carbon, but this oxygen here is now negatively charged, so this isopropyl stays the same. Copy and paste, like that. Right. Any questions on how I got to this point? Right here. Because it could be tricky on where things are going, and then I could try to make it more clear by color coding these pair of electrons in blue like that, which are going to be these blue electrons. These red electrons here on this bond right here popped off onto the oxygen, which are going to be these red electrons right there, right? Like that. And then this is a dash bond because we inverted the wedge bond that got kicked off. Like this nucleophile here is approaching the backside of whatever this is, which is the dash, which is why the bond is formed in the backside, the dash. Okay. This oxygen here gained a pair of electrons, which is why it's negatively charged now with one bond. Okay. Now that's the end of the first reaction. Now we bring in our acid workup to clean up the reaction and protonate and neutralize this alkoxide ion. We're gonna have this alkoxide ion grab a proton. This bond here between the proton ring gas and oxygen will go onto the oxygen, kicking off a water molecule, which is going to give us this final answer here. So in synthesis problems, when you guys see an OR group and an alcohol trans to each other, then I want you to guys think about epoxide opening. And to tell if it's going to be opened in acidic or basic conditions, look at the OR group, because the OR group is going to be the nucleophile, right? Because if you track this oxygen here of the alcohol, that oxygen of the alcohol is going to be the epoxide oxygen. So this epoxide oxygen here is the oxygen of the alcohol. But the OR here, right, is coming from the nucleophile. And if you see that the OR group is on the less subcarbon compared to these 2 carbons right here, you know you're gonna be in basic conditions because the basic conditions attack it on the less subcarbon for synthesis. I'll make this more clear when we go over actual synthesis problems, but let me go over acidic conditions after this. And then we'll do Grignard reagents, redox reactions, and then synthesis problems.
Are you posting the 8B later?
Yeah, I am.
Second session?
Yeah.
Is that like gonna be posted today or?
Most likely tomorrow morning. Yeah.
Sounds good. Because I think Zena's coming to that, and I was gonna ask her if she could like just FaceTime me or something.
Oh, okay. Yeah. But this will be posted tomorrow morning.
Okay.
Yeah. That's good. Yeah.
Do you have to use CH3OH or can you just like use water or something?
It's the basic solvent.
Oh, so the solvent here would most likely match the nucleophile. And because the nucleophile is a methoxide ion, we want to use methanol to avoid any like side reactions.
Okay.
Right.
Action.
Yeah. Right. If you use water here as a solvent, the nucleophile would most likely be hydroxide ion, OH minus. Right? Because the protonated version of hydroxide ion is water. So if you use NaOH, the solvent would be water, H2O. And this R group doesn't have to be methyl, it could be an ethyl group. So if you use ethoxide, the solvent would be ethanol. Okay. Now let me go over acidic conditions. So in acidic conditions, I'm gonna use a basic epoxide here, but we'll work through more complicated ones. Let's see here. Let's use the same epoxide as before, but this time the reagent is gonna be ethanol and acid, H2SO4. Okay. In acidic conditions, you're gonna see like partial positive charge or fully positive charge. It's gonna do the opposite of basic conditions, where it will attack the more subcarbon. And it will also invert stereochemistry. So acidic conditions is kind of weird because it has SN1 property, which is where it attacks the more subcarbon, and SN2 property, where it inverts stereochemistry. Right? And the reason why the acidic conditions will attack the more subcarbon is because that's where the most stable carbocation would be at. The more substituted the carbon is, the more stable the carbocation is. Right? So if this acid was not here and you just had this alcohol with this epoxide, there would be no reaction. Because this alcohol is a stable molecule because it's neutral, and so it's going to be not reactive. Right? We got to activate the reaction by adding an acid catalyst here, which is H2SO4. So in organic chemistry, acid-base reactions are one of the fastest reactions you can have. So because we have a strong acid here, sulfuric acid, we're going to look for the most basic atom here, which is this oxygen of the epoxide. So the first step here is to protonate the epoxide using the strong acid. Right. Making this oxygen positively charged because it now has 3 bonds, 1, 2, 3, and 1 pair of electrons. Now, this is considered a good leaving group now, right? Because it's positively charged. So let's say this bond here breaks off and goes onto that carbon, forming a carbocation here. That's a secondary carbocation. If this bond right here breaks off and goes onto the oxygen, we would have a tertiary carbocation. Which carbocation is more stable, secondary or tertiary? Tertiary, because it's more substituted. So there's a bigger positive charge at this more substituted tertiary position compared to this less substituted secondary position right there. Right? So that's why in acidic conditions, we want to attack the more subside because it has a bigger positive charge. It's a stronger electrophile for this nucleophile to attack. Right? So we're going to have this nucleophilic alcohol attack this carbon. Invert stereochemistry, where the new bond would be dash, to give us this intermediate right here. This wedge bond here stays the same, right, because nothing touched this carbon. This alcohol here, OH, is this OH that was positively charged, but it's now neutralized because it gained a pair of electrons from
Can you use
that bond.
H2SO4 instead
To
of OH? Like to take off the positive?
Oh, like if you use HSO4 minus, like
Like H2SO4, can you use that or no?
H2SO4 is a strong acid, so it cannot deprotonate this hydrogen, but you can use this conjugate base of the H2SO4, right? Because like once we protonate this oxygen right here, we kick off HSO4 minus conjugate base.
So the bottom left right there is supposed to be O minus?
This one here is neutral. This one here is positive charge.
Okay, so you just
Oh,
have like another neutral.
Yeah, for this oxygen or this oxygen here.
The oxygen.
On the bottom is neutral. It's not O minus, neutral. Neutral alcohol. Neutral charge. No positive charge, no negative charge. There's a partial negative charge though. Like a partial.
Oh, I see what you did. You already used the H2SO4.
Yeah, I already used the H2SO4 at the top to protonate the oxide oxygen. Right. Right. And that would give us, let's say, this needle bond here that is a dash because we invert the wedge to this oxygen right here. So if I start with this oxygen here and dot with this carbon here, that's the starred oxygen, that's this dot carbon, where this is the needle bond between the starred oxygen and dot carbon. And it's dashed because we inverted the wedge into the dash. So the isopropyl would also be inverted, so the isopropyl here would be a wedge. And then this oxygen here, that attacked this carbon is this oxygen. We see that it is attached to an ethyl group, so we draw that ethyl group there, and a hydrogen, and a hydrogen. So because we see it has 3 bonds, 1, 2, 3, and 1 pair of electrons, the formal charge of this oxygen here is going to be positively charged, like that. Right. Now, we can clean up this positive charge by bringing in the conjugate base that we created in the first step as the base to deprotonate this alpha oxonium ion and neutralize it by giving it to this pair of electrons right here. Yeah, where we see that we have an alcohol and OR adjacent to each other, right next to each other, and they have a trans relationship with each other. Right, one is wedge, one is dash, and because we see that, we want to think about epoxide opening, but we see the OR as a nucleophile, right? And we see that compared to like these 2 carbons right here, this is the more subcarbon, and because it's a more subcarbon, we attack it in acidic conditions. Because the more stable carbocation is at the more substituted position right there. Yeah.
You said that this is SN2 character, so the reaction happens by SN2, like the epoxide.
Yeah, the reaction happens by SN2, where it attacks the carbon, backside attack, invert stereochemistry. It's not SN1 because we don't form a carbocation here. Like this doesn't leave by itself, forming a carbocation right there. Because if it did, this would be flat and planar, where the alcohol can attack on the top side, giving us a wedge product, or the backside, giving us a dash product right there. Right? And we won't get that because we would get this exactly since it's gonna do inversion 100%. Yeah, SN2. Yeah.
Why does the substitute side have this bigger positive charge?
Yeah, the more substitute side has a bigger positive charge because you know how this is a good leaving group right here? The positively charged oxygen. Imagine like these 2 bonds here, like one of it can leave. If we kick this bond off and go to the oxygen right there, we form a secondary carbocation. If we kick this bond off and go to the oxygen right there, we form a tertiary carbocation. And because the tertiary carbocation is more stable, the positive charge will want to reside in the more substituted position because it's more stable there. And because the more stable positive charge is at the more substituted carbon, right? That's why we attack the more subcarbon. Acidic conditions is more complicated than basic conditions because there's more steps to it. But for epoxides, you won't always see a wedge or a dash. like you might see a flat bond, you can still invert that flat bond, which I'm gonna go over in the next example.
Do you want to use one? Sure. Maybe. Yeah, I'll try.
I'll give you guys two problems here. Number one, and we have
You can just use mine.
and the second one will have
Is the Turk beetle facing towards us?
the Turk Beetle. Oh, it's gonna be a dash. So when I draw a squiggly line, that's gonna be a dash. Dash. So facing away from you. Okay. I think you guys could try this, and then I'll walk around if you guys have any specific individual questions to help, and then I'll come back to this in 5 minutes.
I think we can squeeze anything. Yeah? Yeah, I mean, you could just take a chair. I feel like
I really got you in the moment. Oh yeah.
Also, now we can talk. What is I'm trying to reverse problem.
Got you.
I think that is.
I was like, wait, you were about to gaslight me. In 2 more seconds, I was like, wait.
Okay, so always just like
So,
the
if you look at the
important
first
one,
one,
right? This is
When you see
Google
an A, what charger?
this to like out there
Oh, are
or
you
some
thinking
shit.
because you see the
The first thing
So
I
when you
would
see
do
stepwise, like
is I would this is just a salt.
explore step two, you look at this as
Get like a chair.
a circle long lane. Right? So the thing that's reacting here is
You
this
can like
whole
sit
six
kind of to the side of the chair. Oh, I see. You're not that tall.
Yeah. Yep, of course, Hasna. It's very nice to meet you, like in person.
Okay, thanks for coming all the way.
Yeah.
Did you stay far or?
San Jose.
Oh wow, so that was quite a.
An hour and a half drive. But I picked up Brad, he lives in Elk Grove, so he was like asking him up and come over.
Oh wow.
Yeah.
Okay.
Yeah.
Why is it just around here? Could we squeeze right here? I missed my iPhone.
Yo, let the process work.
Am I just kind of weird? Is I look like a Chick-fil-A box? Like, that's a little bit. I think I have
The box with the hoodies.
Yeah, like the things coming out, they look like the fins of the Chick-fil-A.
I think you're hungry. I'm hungry,
No, I'm trying to make
but I don't want to eat here.
Did you guys go over?
No, I was
I just figure out where to do these.
I already forgot what happened.
I know it's hard.
Or like,
They're gonna be like, oh, you didn't draw that around the
How did you determine it's basic?
because it has a sodium. This is the cation, right? The sodium is gonna get the
So whenever you see like an epoxide, you have to determine first if it's basic or acidic.
yeah. The acid determining if it's acidic condition is pretty easy because it'll be like an acid H2SO4. That's an acid. Like that's most of them.
Oh.
And then this is basic because the sodium would get the positive charge, and this gets. That's what I'm saying. Also, like
You can just do the two fingers. Okay. Like, look.
I'll have time to like I'll be driving there. And then that will become negative. That's what I drew over here. So I can like sit. It's gonna attack the less soft tissue. Then what? It sucks. It's like wow, like I get it, but then I didn't really do like so midterm 3 is maybe the best, but I did like the most like so it's like solid. Like it was
I'm confused. Where did I study all
and
that?
then
It's so much.
I don't know. I'm like I'm doing it's a lot.
Yep, and you're gonna drop the carboxylic acid.
Yeah, the midterm too, but I wanted to know like for like the final I need to like actually understand that stuff. But the derivatives, oh my god. Like
Because there's so much different reactions going on.
like if you look at this though, I mean that's pretty much like all I need to know, right?
Yeah, we have it separated like that.
Farahot
So
speed
base
and reactions too.
Huh?
Did Farahot speed read and reactions too?
The reactions. This is like
A bit, yeah, but I don't think we learned
then like
this.
I looked at the
My reactions were so dead run. Like I don't know what's going on anymore. There's no time to
so I
watch
needed
work.
to learn how to apply these
Like,
to
I
actual
don't know what to do. I've been trying to learn from like YouTube and stuff, but it's kind of like failed.
Yeah, I don't know that many good OChem YouTubers. I just watch Brian's videos.
Is it online? Oh, you said online.
Online.
There's like 36 reactions here.
I don't definitely.
Like once I like study another, I forgot the other. And I study the next and forget the one I learned before.
I'm so cooked for this class.
I don't think this is right.
Just one more quarter of OChem.
What did you do?
I don't know. It's nice to meet you too.
That's right. Isn't this more stable?
Yeah, but this
So
is
you do
basic.
this and then you attach to that.
This is basic, so once the less is distributed, how,
It's gonna be at 2:30.
because there's less steric hindrance. It's hard for this to fit into this because this is all SN2 properties. I'll get that done before I go anywhere.
Okay.
For sure. And then also I'm probably gonna.
So like
I don't know.
so this charge right here, it's attacking this.
Because this carbon is attached to oxygen,
Oh, yeah,
so it's
yeah.
partially positive. I haven't done that.
Is,
Have you heard
is
the
this
recommended orders?
well? This has the other stuff.
This is also partially positive, so you would have to choose. And in basic conditions, you follow all SN2 rules, which is it's harder for this to fit into this place since there's already stuff there. So
So
this,
this moves into there. That becomes a partial negative.
yeah, we're all good. Yeah, and then you add that, I guess, but I kind of.
Let's say art.
Yeah.
What if like
Me too. I struggled falling asleep, and then I was like, good, I was asleep, and then I woke up not being able to like breathe out of my nose. So I grabbed a tissue and I'm like blowing my nose, and then I turn on my flashlight, and there's blood on the tissue. I had a bloody nose. I haven't had a bloody nose like in the middle of the night since I was like 9 years old. You know when it's like,
that's a really bad though.
and then it's blood.
I live with her now because like
That's
it's
good.
like
You're just
sad.
so done with. Wait, don't you live at West Village?
Yeah.
Yeah, that's what green is.
Oh, I don't know what's called.
Well, because it's like Green and Soul are both in West Village.
I have
I was saying last night, but
They
then
don't even have food. So it's like, should I just go back to my apartment? Because I'll start both ways.
we don't have food. We have so much salmon.
I know, but you guys have dinner, but not
My
breakfast.
apartment is huge. Like you could have the whole living room to yourself.
That's crazy.
I have like the L-shaped couch.
Where do you live?
I live in South Davis at Axis.
Did you do the first problem?
I don't know how to do it.
Because I got like this, but like that doesn't look like a real thing.
I think you're supposed to have a triangle somewhere.
Well,
Like
I
it
broke
connect.
it, right? Because this is where breaking the epoxy.
Girl, I don't know. I don't think I learned this.
I don't know. I wanted to live close to bike, but every time I get a bike, it gets stolen. So I don't know what to do anymore.
After you said you got your bike stolen, I was very nervous about mine and I rode it home.
Oh, I hate my bike. I hope
I
someone
like
steals
never
it.
leave
love
my
my
bike
bike.
overnight. I carry it all the way to the 3rd floor, and I took really good care of it. So it was really sad when it got stolen at 7 p.m. Like in front of a lecture hall. Like,
Oh,
it was
at Wellman?
Yeah.
Yeah.
It was like
I
at
feel like
7
that's a kind of
p.m.
a sketchy place to leave your bike. I always leave mine at the silo.
at the silo.
Yeah. And my bike has never been stolen. But like since I don't need my bike for the rest of the quarter, it's at home. Rode it home last
Yeah,
week.
I don't know. I just like, cause like she lives in the green. I live like where Porto's at.
Yeah.
So like, there's no bus that connects from Porto to the green. So I have to go all the way on campus.
Only on the
bus.
weekend, yeah.
Yeah, and then I have to take another bus to get to her, and so it's like really annoying commuting without a bike because it's like
Yeah.
adds on like extra 20 minutes. It feels. Maybe it's less than 20 minutes, but I think it's.
No, I hate how long the buses take.
Yeah, I like, and then I got another bike. I like my, it basically is like the same bike as my first bike that got stolen. It's kind of funny. This is all gonna be recorded.
Oh yeah. Wait, no, I've been like swearing and saying weird shit.
It's
No, actually,
Melina.
I think he cuts out
touch
the. I think he cuts out the part where he tells you to practice.
Oh, you know the water bottle I bought you arrived. Oh yeah, that's something cute.
Yeah, I got a new water bottle.
Yeah, dude, my water bottle's like this big, and then every time I put on my backpack, it falls out, and the mouthpiece is exposed.
Yeah,
So,
I hate the exposed mouthpiece. That's why I got this one. So that way the straw like stays hidden.
What do you mean by exposed?
Like the straw was just out in my old bottle. Like it was just like this, and the straw's like that, and then you drink from the straw.
Oh yeah,
Just
yeah,
like a-
like here you can touch, and it's so sanitary, you know.
Yeah.
Like bro, it's just like mine is white too, so you can see how dirty it gets. So I had to wash it every
Yeah.
day, and still didn't feel like enough. Like
My
I needed
bottles kept falling on my backpack, so I bought a new backpack. And then I realized the problem is I should just not have 40-ounce water bottles.
I'm actually moving to her place. It's like weird. Like I have to bring more. I'm basically living with you.
Yeah.
I'm bringing more clothes to her place. I'm having half of them at her place, half of them at my
I have
place.
to buy more Tide Pods so I can do your laundry. Okay, wait. Where? Oh, he's over there. I'm gonna wait for him to come here because I need his help. What's going on? Oh, let me try the next problem.
I just know the next one inverts stereochemistry.
They both will, because they both are SN2. It's just the one with the acid is weird because it also has some SN1.
I think what I'm gonna do for studying for OChem today is I'm gonna do like reactions. I don't really know reaction. I'm not gonna lie. Like every time I try to watch something, I like fall asleep because it's so boring. But like
I just know I'm good at
Let's get back to
I want to
these
do
problems over
discussion
here.
and the reactions. Discussion.
So, for number one, a very important thing here is that this is stepwise. Step one, step two. They're not together, right? Because if this wasn't here, like number one, number two, that would imply that these reagents are together, right? But we know that sodium is positively charged, and this OR group is negatively charged. So we have an OR minus, and let's say step one, step two was not there. This strong base OR minus here would react with the H3O plus if they were together, but they're separate, right? So when you see step one, step two like this, ignore step two. Just look at step one to determine if it's in acidic conditions or basic conditions, right? And because we see negative charge right here, we're in basic conditions, right? Because if you just look at this, you might be confused, like is it acidic conditions or basic conditions? But we don't look at this, we ignore step two, right? And then this OR here wouldn't attack the left subside, it would get protonated by the H3O plus if this was together. because acid-base reactions are the fastest reactions, right? So if we ignore step 2 here, we see that we have a negatively charged alkoxide ion, saying that we are in basic conditions. And in basic conditions, what carbon would we attack? The more or less subcarbon?
Less
Less
substitute.
subcarbon, right? Which is this less subcarbon here. And invert the stereochemistry of this bond right here. But you notice how this is not a wedge or dash?
Yeah.
Like we can't easily say wedge to dash or dash to wedge. What we have to do is make this bond of the epoxide, which is the base of the epoxide, the reference bond. And you notice how these two bonds here are going up, right? When we invert stereochemistry, the new bond would go down of the bond, right? So let me just draw that here in the mechanism to make it more clear. Right, so let's say we have this. This bond here stays untouched because nothing attacked that carbon. This bond here stays up. And this will be negatively first because this oxygen gained a pair of electrons. Copy and paste the wedge and dash over here. Okay. Now, this bond here that we broke is going to go onto the oxygen, giving that oxygen a negative charge. This OR group will attack at the backside, making a new bond going down, right? Reference to this base of the epoxide right here. Right. So we cannot do like wedge to dash or dash to wedge, but we can invert the stereochemistry of the flat bond still in relation to the base of the epoxide, like that. Right. Where, let's say this was the dot carbon, this is the starred oxygen. Right. This is the new bond between the star and dot carbon. The oxygen here is attached to an ethyl, so draw the ethyl group like that. The dashed isopropyl stays the same like that. Okay, and then we just clean up by bringing in the second step now. After we do the first reaction, we do the second reaction, add acid in the solution to protonate the alkoxide ion and neutralize it. Where we see the OR group and OH group are trans to each other in reference in relation to this baseline right here, right? And the OR group is on the left subside because we are in basic conditions there.
So I get it for the chain being added, but I thought it would still invert the tert-butyl and then the hydrogen, the stereochem for them.
The tert-butyl and hydrogen right here.
Yeah, I thought you would at least invert those stereochemistries, even if the chain doesn't.
So we wouldn't invert this chemistry because let me do R Nesper here. So let's say this is the Kara center. This is priority number 1. And then there's 2 tires over here. This is number 2. This wait, no, this is number 2. This is number 2. Because this is attached to 3 carbons. This is attached to 2. 1, 2.
No, the other one, the left one's 2 because of the oxygen.
Have to review that.
Oh, right. It's attached to the oxygen right here. Yeah. I was like 3 carbons, 2 carbons, 1 oxygen. 2, 3. And then 4 is the hydrogen right here. So that's going to be. It looks S. Right, so it's actually R.
I just want my hoodie, bro. I'm cold.
So it's R. We go over here.
I have too many hoodies, but I was like, man, I love hoodies.
And then it's R. It's S. So we did invert stereochemistry from R to S, but hopefully it won't always. Yeah. Well, actually, this way is not a good way to do it because whenever you do SO2, it will not always invert R to S or S to R.
Wait, isn't it? Isn't it? Aren't you going from R to S? It should be It's originally R, and then you flip it because of the hydrogen, so it's S now.
So
Oh wait, is that what you're saying?
originally R, but it's S now. Yeah,
Oh,
it's S
sorry.
now. Yes, yes. Yeah, but this way isn't a good way anyway, because whenever you do SN2, it doesn't mean that it will always invert from R to S or S to R. Because an example of that would be something like this, where if you have, let's say, this good leaving group, and then you react it with NaCN. What's the R and S of this right here? This carbon right here?
It's R.
1, 2, 3, R. Yeah, clockwise. Backside, like the lowest parallel group is on the backside already, so it's R. When we do NaCN, we're gonna kick off this good leaving group, invert stereochemistry, and have a dash like this. CN. What's the chiral center of this one right here? What is, wait, 1, 2, 3, 4. It is S, yes. So in this case, it does invert stereochemistry. I'm trying to think of a reaction where
I think if that oxygen on the end, I think that would.
this one right here.
On one of the ends, I think that would fix it. Yeah.
So let's say this is an ether. 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 Now this would be 1. Wait, actually no. This is the 1. This is the 1. This is 2. This is 3. 1, 2, 3. S. So this is S. 1, 2, 3, S. Yeah. And say this is 1. This is 2. This is 3. Oh no. This is 1. This is 1. This is now 1. This is now 1. This is 2. This is 3. Going this way looks R, but it's actually S. Yeah, so it's actually S. So in this SN2 reaction right here, we did not invert the S to an R. This chiral center here stays as an R, right? So this point of the problem here is just to say that not all SN2 reactions would invert R to S or S to R. Because we see in this SN2 reaction here, the S chiral center stays as an S chiral center, right? But in the problems where I've seen epoxide opening, I've seen that when we invert this bond right here, these bonds here do not invert, like the dashed butyl do not invert, right? We just invert the flat bond like that, right? Okay. Any other questions on this problem here?
If we were like predicting a product on the exam, can we leave it like that, or do we need like rotate it? Like,
Oh, for this right here?
yeah.
You can leave it like this for leave-ins. She or the TAs will be able to read this and give you full credit for this right here. Yeah. Fairhat will give you multiple choice questions. So just like choose it based on the multiple choice questions. Yeah. Just note the important thing here for that is that the OH and OR are trans to each other, right? And then if you see that in the multiple choice, that's very important. The other important thing is that in basic conditions, we want the OR at the less subcarbon. So when you see that, choose the answer for the exam. Yeah. Oh, so for leave-ins, you would have to, like, on the answer key or the problem set, she'll make you rotate it in a way where the longest carbon chain is flat bond, like that, to get the right answer on the problem set. But on the exam, like the final exam, you can leave it like this. Yeah. But for the problem set, like this would not be the answer for the problem set, for leave-ins problem set. You would have to rotate it where you get the longest carbon chain as a flat bond.
What time is it?
140.
Yeah.
Let me check on my iPad.
To like based off of that, you can't even trust stereochemistry. Then how do you know if you're doing it right?
Yeah, so whenever we invert flat bonds like this, the other wedge and dash bonds will stay the same because let's see here.
If you're to draw it out 3D, like
Yeah.
would it make more sense if you were to like try to like
Yeah, it would make more sense because let's say this dash alpha group is facing away from you, right? And then just imagine it visually. This isopropyl is facing towards you, and then this dash tributyl is facing away from you, right? And then the thing that we're interested in is gonna be this flat bond right here towards the plane, which I'm gonna highlight in blue like that, which is this flat bond right here, right? Everything else is gonna stick away from the equator, right? When the outside side here, like to make it more accurate, the arrow would actually come from the back, right here, behind this carbon. And then when we're going from the back to create a new bond right there, that's gonna be this new bond right here, kicking this up right here, right? So this bond here is now onto the oxygen, creating an O minus right here, right? The other groups right here will just stay in place, like it wouldn't change. Like I want you to just think about this flat covalent bond right here. That's the only thing that's gonna change, where we see that this OR group is going on the backside, creating a new bond on the back, right here. Yeah. Mhm. But if you think about it in like the wedge dash form, when there's a wedge, the nucleophile will approach it on the backside dash, which will invert the stereochemistry and invert everything else.
Okay.
Yeah. Yeah, that's good. That's good. Because like, there's a lot of like visualization going on for these stereochemistry stuff there. Yeah. Okay. Now for this one over here, we're in acidic conditions because we see strong acid H2SO4 here. And what was the very first step of the mechanism for acidic conditions here? Oxonium ion, protonated epoxide to get the oxonium ion. Okay. Now once you have this oxonium ion here, which is the good leaving group, which carbon would be the electrophile? Which carbon would have the more stable positive charge?
The more.
Yeah, the more subcarbon, which is this carbon right here. So that's our electrophile right there. Now the nucleophile, which is this butanol, is going to attack this more subcarbon because the bigger positive charges there. Break this bond, go onto the oxygen right there, and invert stereochemistry. Right, and we're gonna invert it in reference to this bond right here, and we're just gonna look at like these bonds right here. Just going on the back side of this, so it's gonna become a bond going down. This wedge isopropyl and dash methyl and wedge methyl here will just like stay in place. But when we do the backside attack right here and invert stereochemistry, think of it as a face. Like it's just gonna approach this carbon, making a bond back here, like that. Right? Okay. And that's gonna give us this right here. OH, and then this is O. I'm just gonna draw this first because everything else is decoration. I want you to ignore everything else. This is the thing that's gonna be important here. Right, this is the reference one here. Where we see that this right here is the new bond going between this oxygen and carbon approaching on this side of the reference bond, which is why this new bond here is on the back side. This bond here stays down here because nothing touches that carbon. Everything else here will stay in place. So copy and paste like this. And then last step, use the conjugate base that we formed to deprotonate and neutralize the positively charged oxygen. And where this is the most important part right here, the alcohol and OR are trans to each other, and because we're in acidic conditions, the OR will become the more subturbine, where there's more substance on this carbon. Copy and paste.
I don't think you do that.
Yeah. Yeah.
Is that for like the flat ethyl chain that you added?
Yeah.
Or ethyl or can you like, or are you just doing that just so
They're not hard. They're very simple.
Ethyl oxide.
The one where it's under the trans label.
Under the trans label.
Yeah, right.
This one right here?
Yeah, so you purposely placed it on the bottom. Can you place it on top? No, does it?
Oh, this one right here? Oh, in this case, we don't want to place it on top because we see that those would be cis in reference to this line right here.
Oh, so you always want to try to make it so it's trans.
Yeah, we always want to make it so that it's trans. The OH and OR are trans to each other.
Okay, because that's what I was gonna ask. Like for example, the one with the acidic. You know how you attacked it with behind the wedge? I was gonna ask like, why can't you attack it between the wedge and the dash? Is that because of trans again, like you just said?
Yeah, it's because of trans. We want to be trans, trans to this bond that's breaking right here. And this bond that's breaking right here is not a wedge or dash, so we don't want to approach on the wedge or dash. We want to approach it on the backside of this flat bond, which will be flat on this direction right there, like that.
What if you had like a more, like a bigger group? Like let's say when you're attacking, does it? So wait, sorry, I'm trying to think of the words.
Yes.
Do you always have to consider the one you're attacking as affecting the trans or cis, or could you? Let's say there was already a big group on the pot side.
Yeah.
Do you just look at that instead then?
Like a big bulky group like a turbulent here or something
Yeah,
like that. So you don't look at that, you ignore that. You're only looking at the bond that's breaking up.
Okay.
Right. Look at the bond that's breaking up. You want to go trans to that, on the backside to that.
Yeah, but that's wait.
Yeah, yeah.
Like, but do I look at? Do I look at like for example like right here like?
Yeah.
How do I know I look at like because wouldn't this have more of an effect on this?
Oh, like with that, we just ignore. Like that one.
Oh, so you only care about the one you're adding in?
Yeah, we only care about the one we're adding in. Yeah, yeah. Those ones, think of it as like just floating away into like the space.
Okay.
Like, not interfering with the reaction. Yeah. Yeah.
It would make my life easier.
Okay.
That was like kind of the focus of betting I can do it. I can do it. Unless he says GCW and then the next page is just like on this.
This one right here. Do we have to draw that step in the mechanism? Oh, so this whole thing right here
I would say no.
attracts this carbon, but specifically the oxygen atom, which is this oxygen atom right here, creating this new bond. But this oxygen atom has a terbutyl group, which is a terbutyl group, and a hydrogen still, which is this hydrogen right here.
Oh, so that's SN2 mechanism.
Yes, SN2 mechanism.
So hydrogen attacks here and
You know what's annoying? I actually know that. So
Yeah, right.
yeah, exactly.
well, there isn't
Yeah, there's some hydrogen there, right? Whereas if you look at the basic conditions, right? This OR group, this OR group here attracts the less subcarbon, which is this entire OR group right here. But because this whole thing is attached, the hydrogen
It
is there,
depends on
that's why
what they
it's
show
positive
because we
charge.
didn't really learn that many acid-base reactions.
Yeah. Yeah.
And basically what I just told you.
Yeah.
So would I only do that typically for these epoxide openings? Because my understanding like usually you only look at the ones
I think they're just
most
scattered.
or not the bulkiest groups when doing system. So is it just a special
Yeah.
exception?
This is special exception for epoxide opening. Because it's weird in acidic conditions, because you know when you do SN2 backside outside, you want to look for the less substituted position, right? You think of steric hindrance. This one here, epoxide,
You need to know
would be the
relative acidity of alcohols. You need to know like the Gura reagents, preparing alcohol, summary methods for preparing alcohol, substitution, elimination, oxidation. Yeah, basically everything here. Chapter 13, like all of it.
And that will be cover everything.
Not everything. That's just alcohol.
Actually,
And
read
there's
that.
ethers and epoxides. There's like 3 things.
They have the edges and epoxide.
Okay, yeah. So 13 and 14 should be all of the main reactions.
And then synthesis at the end.
Synthesis is just like putting all the reactions together.
We're covering like almost the entire semester.
This is what happens when you treat things because it's actually very hard.
I'm never going to Thanksgiving.
I didn't do it. I stayed here.
So I want to go over 3 different reactions synthesis and then do synthesis columns. First one,
I went home last year and I got nothing done. So this year I was like, I'm staying in Davis.
I'm putting. I forgot what I was saying.
and then
I forgot about my homework, so I missed like physics, like drills.
It's okay. It's only worth like 0.1% of your grade. Like 1 out of the 3,000 points.
I'm telling myself next quarter will be better, but I don't think so.
I guess it depends on the instructor because physics 9B is weird, but not near as difficult as 9A.
9A, like you can just like not study and you'll still like pass because everyone fails.
Literally.
That's what I did. I actually got the value by guessing. I studied and I got below average.
Yep.
You just have to know how to guess.
Because the conceptual and multiple choice are hard.
in Gen Chem, you guys learn about oxidation and reduction as like either oral rig, right? Like oxidation is the loss of electrons, or reduction is the gain of electrons, or Leo the line says GER, like loss of electrons is oxidation, gain of electrons is reduction.
Oil
right?
rig.
But in OChem, I don't want you guys to think about it like oil rig or Leo the line says GER. I want you guys to think that oxidation is going to be the gain of bonds to electronegative atoms, and or you can think about it as the loss of bonds to hydrogens.
I don't care about
Reduction is the exact opposite. Reduction is going to be the gain of bonds to hydrogens. Or think of it as the loss of bonds to electronegative. Okay? So the things that would oxidize things, right? Making things have more bonds to electronegative atoms or lose bonds to hydrogen atoms are going to be called oxidizing agents. Right? And there's weak oxidizing agent, which we'll see it as PCC, CH2, CO2. This CH2, CO2 is an aprotic solvent. It's not going to interfere with the reaction. PCC is the one that's going to do oxidizing. So when you do synthesis, you could just write PCC. You don't have to write CH2, CO2. You can if you want to, but that's not going to interfere with the reaction. Right? Or you see a strong oxidizing agent, like drones, which are going to be like the chromium ones. You can see that as CR, water, or Na2, CR2, water, or H2, CR4, H2SO4. The most important thing here to see in Jones is the chromium, and a lot of oxygens, making it a strong oxidizing agent. The rest is acid and water. Now, we're gonna talk about oxidizing alcohols here for 1A, right? So we can have a primary alcohol, we can have a secondary alcohol, or we can have a tertiary alcohol. Now, this right here is a primary alcohol. This right here is a secondary alcohol. And this right here is a tertiary alcohol. And the reason why this is a primary alcohol is because the alpha carbon, which is the first carbon attached to the alcohol, is attached to one other carbon. This is a secondary alcohol because the alpha carbon is attached to two other carbons. This is a tertiary alcohol because the alpha carbon is attached to three other carbons. Okay? Now, primary alcohol here is going to be the most difficult one when we talk about oxidizing agents because they lead you to different answers. If you use PCC, you can write this if you want, but it won't affect it. You're gonna oxidize the primary alcohol into an aldehyde. If you use drones, which you can see as any of these three forms, you're gonna oxidize the primary alcohol into a carboxylic acid. Okay. Now, the reason why PCC is a weak oxidizing agent is because, well, how many bonds to hydrogen do you see on this carbon here? 2, correct? How many bonds of oxygen do you see on this carbon right here? 1. If you look at the weak oxidizing agent, how many bonds of hydrogen do you see on this carbon here? 1. How many bonds of oxygen do you see here? 2. So we see that we traded in 1 bond of hydrogen for 1 bond of oxygen, which is oxidation because we gained a bond to oxygen and lost a bond to hydrogen right there. Right? Whereas if we use Jones, we lost 2 bonds of oxygen for 2 more bonds of oxygen, which is a stronger oxidizing agent because we did more of that. Right. So this is just like a way to understand it here. You don't need to know the mechanism of how to convert this to this, like the arrows, pushing mechanism. You just need to recognize the reactant and the reagent in the product that gets formed for synthesis. Okay. Now, secondary alcohol is easier because it does not matter what oxidizing agent you use. You can use PCC or Jones, it does not matter, right? Because we only have 1 hydrogen to trade in for. Right, there's only 1 hydrogen right there, and you're only gonna get a ketone from a secondary alcohol. Ketone, right? Because we see that this carbon here lost a hydrogen bond and it gained a bond to oxygen right there. Okay. Now we see that this tertiary alcohol here has no alpha hydrogens, so we cannot do oxidation of a tertiary alcohol at all. So if you use PCC or Jones here, there would be no reaction for the tertiary alcohol. And not. Because oxidation is this right here. There's a weak oxidizing agent PCC, strong oxidizing agent Jones, and then the difference between primary, secondary, and tertiary alcohol.
It condenses pretty nicely, but a lot of it's.
Now, reduction is the exact opposite of oxidation, and the things that would reduce things are called reducing agents. And there's also a weak and strong reducing agent. Reducing agents. Now, in 1 A, you learned about sodium borohydride, NaBH4, with some alcohol, ROH, like ethanol or methanol. You could see that this as well. First step, NaBH4. Second step, acid workup. This is more for Fahrenheit. This is more for Levens. Now, the strong reducing agent is lithium aluminum hydride, which is going to be LiAlH4. Second step, acid workup. Now, we're going to talk about aldehydes, ketones, and carboxylic acid. Oh, but before I go over that, I want to show you guys this right here. We can oxidize an aldehyde into a carboxylic acid using Jones. Right? If you have an aldehyde and you want to make that into a carboxylic acid, you can do that using a strong oxidizing agent, Jones. Now, these are going to be the carbons that I'm going to look at. Now, for an aldehyde, you could use sodium borohydride or lithium aluminum hydride. Second step, H2O plus, to get this primary alcohol here. Because we see that this carbon here gained 1 bond to hydrogen and lost 1 bond to oxygen. So we reduced this aldehyde into a primary alcohol. Ketone can also be reduced by both NaBH4 or LiClH4, cyclosilate H3O plus, to get a secondary alcohol. Right? Because we see here that this carbon here had 0 hydrogens, 2 bonds to oxygen, but when we reduced it, this carbon now has 1 bond to hydrogen and 1 bond to oxygen. Now, if you look at the carboxylic acid, we see that it could do resonance, right? If we have this pair of electrons, make a double bond here, pushing this double bond to oxygen like that, that's going to form a resonance structure, which would it increase or decrease the stability of this carboxylic acid if it can do resonance? Increase, right? And if it's more stable, would it be more or less reactive if it's more stable? Less reactive, right? Because it's more stable, more happy, it wouldn't want to react with anything, right? So this cannot be reduced by sodium borohydride, a weak reducing agent, right? We would need to use a stronger reducing agent, lithium aluminum hydride, to be able to reduce this carboxylic acid into a primary alcohol. Right? So let me show you this here. Stronger reducing agent reduce the carboxylic acid into primary alcohol. Weak reducing agent, NR. So Liebens has tested like this before, where she tested, if carboxylic acid can be reduced by sodium borohydride or not. The answer for her would be no reaction. No reaction. Okay. And we see that this is reduced because this carbon here lost 2 bonds of oxygen and gained 2 bonds of hydrogen. Not 2 bonds, it could only be 1 bond, right? Like if you look at this aldehyde right here, this aldehyde lost 1 bond of oxygen and gained 1 bond of hydrogen. Because we see that this carbon here already has 1 hydrogen, but now it has 2 hydrogens. So it could also be 1 as well. So this would be 2. The 2 would be the strong ones, like a strong reducing agent. The weak ones would do 1. If you look at PCC versus Jones, PCC only trades in 1, right? We see that this carbon here had 2, but if we use the weak one, it now only has 1. It had 1 oxygen bond, but now has 2 for PCC. If you use a strong oxidizing agent, it could do 2, like trade in 2 hydrogens for 2 bonds of oxygen, like that. So that's the difference between weak and strong agents. What is it?
It's 204.
Okay, 204. Now, for organometallics, right, you could see it as Grignard reagent, or you can see it as organolithium. Same. Well, not the same thing, but they do the same chemistry, right? Organolithium is RLi, Grignard reagent is RMgX, where X could be chlorine or bromine, most likely bromine. So, let's say we have some random Grignard reagent. Let's talk about how to prepare it first. Let's say we have this halokene right here, and we do Mg ether, any kind of ether. What is the partial charge of this carbon here directly attached to the bromine? Partial positive charge, right? Because it's directly attached to this electronegative bromine atom. But if we do Mg ether, the Mg will just insert itself between the bromine and carbon, creating an MgBr, right? Which would be like this, where now this carbon here, think of it as being more electronegative than this magnesium. And if it's more electronegative than the magnesium, it's going to pull or withdraw electrons from the magnesium, making it negatively charged. And this Grignard reagent right here, I want you to think of it as a strong base, strong nucleophile. But what do you guys think is gonna be better? Base or nucleophile? Which one's faster? Base, right? So if there's an acidic proton anywhere, you go for the acidic proton over the electrophile, like a carbocation or carbonyl, right? And I'll go over examples of this, but this is what a Grignard reagent is right here, and I'll show you different reactions here. Let's say we have the same Grignard reagent, and we react it with
Yeah. Oh, sorry, I'm just mad.
Okay. So we know that this carbon here directly attached to the magnesium is partial negative charge, which is a strong, very strong nucleophile. Let's look at the first reaction here. If you see stepwise like this, ignore the second reaction. Just look at the first reaction and see what that would do with this reactant here. Do you guys see any partial positive charge atom in this aldehyde right here? Yeah, the carbonyl carbon, which is the electrophile. Now the mechanism here is gonna look like this. I'm gonna make a box for the mechanism to show you guys what it looks like. This is reaction 1, reaction 2, reaction 3, reaction 4, reaction 5. That's for reaction 1. We see that this nucleophile is going to be labeled as a star. This electrophile is going to be labeled as a dot. I like doing that because that will help me attach the molecules together without losing a carbon or adding a carbon by accident, which I think is the hardest part of this reaction. Right? This nucleophile here is going to attack this electrophile, making a new bond between the star and dot. But we see this electrophilic carbon here already has 4 bonds, so if we gained another bond, it would have 5 bonds, which is not good. That breaks the octet rule. So what we have to do to conserve the octet rule here is to push one of the bonds of the double bond onto the oxygen like that, which will give me this here. Right. Let's say this is the starred atom, this is the dot atom. This would be the new bond here, because the MGBR would dissolve away into ions. It would just disappear. Right. This new bond here was created in this attack. This dot bond, the electrophile, has a methyl group, which I'm going to draw the methyl group called like that, and a single bond O minus. It used to be double bond oxygen, but now it's single bonded to the O minus because we popped the double bond onto the oxygen like that. It also has a hydrogen, but I'm going to leave that as invisible. Now, that's the end of the first reaction. We then bring in the second reaction, acid effect, once we have this alkoxide ion, which would just clean up the reaction and neutralize it. Which will give us this alcohol here, secondary alcohol. Now, there is a way to quickly predict the product without doing the whole mechanism. You know how I started the carbon directly attached to the MGBR and dotted the carbon with the carbonyl? I'm gonna... So this star carbon here is this star carbon here with the purple tube coming out of the ethyl group coming out of it. 1, 2, 1, 2. This is a new bond between the star and dot carbon because we did the attack. The dot carbon's carbonyl here, the carbon number 1 oxygen, becomes an alcohol, OH. Everything else is decoration. This methyl group there is that methyl group, this hydrogen there is invisible, like that. We can do the same for this ketone here. Star that nucleophile, draw out the star part of the molecule, which is this right here. MGBR goes away, disappears. Make a new bond between the star and dot. Okay, new bond. We see this dot here used to be double bonded to an oxygen, but we know that oxygen is going to become an alcohol. So I can draw the alcohol coming out like this. And this dot carbon here has 2 methyl groups. It doesn't have to be 2 methyl groups. It could be 1 ethyl group and 1 isopropyl group. Just copy and paste it over to the dot carbon like that. Whatever it is. Now, I'm going to draw the mechanism for the third one actually because this is kind of new. Are we in basic or acidic conditions if we have this Grignard reagent? Basic conditions, right? Because we know that organometallic is a strong base. And if we're in basic conditions and we see this oxide right here, do we want to attack the more or less subside of the oxide? Less subside, which is going to be this carbon here, the dot carbon. Right, so I'm just going to draw the mechanism here to show you. I'm not going to worry about stereochemistry here, but it would also invert stereochemistry. I'm just going to make everything flat and planar just to go over the reaction and synthesis. Right. So, it's going to be star, dot, this is neal. The dot is attached to this group, O minus. And I could color code this other carbon, the morsel carbon in blue, which is this blue carbon right here. Because this bond between the red and blue carbon is this bond between the red and blue carbon. When we kicked off the epoxide, the oxygen of the epoxide is attached to the blue carbon still, which is this bond right there. And we see the blue carbon is attached to the methyl group, which is this methyl group right here. It could be an ethyl group if you want, but depending on the problem. Right? Or you could add it in depending on the synthesis. And then now we bring in the second step, acid H3O plus, to protonate and neutralize the O minus to get into this OH right here. Okay. So we can start this. And I can call it this more subcarbon as blue, which is this blue carbon right there.
Ranner.
Ranner's fun.
How is that like surprise popping into her mouth?
Now, for the fourth reaction here, what do you guys think is going to happen between this nucleophile and this electrophile? What reaction? SN2, yeah. Nucleophile attacks carbon, keep out the leaving group, connect them. SN2. Dot. Neal. The dot is attached to isopropyl, so I draw isopropyl coming off of the dot like that. That's it. Yeah. Okay. Another thing I wanted to point out is that you know how when we open up epoxide in basic conditions, we're used to seeing an OH and an OR trans to each other. It doesn't have to be an OR. It could be an R group. Right. This right here is an R group, and when you see an R group, I want you to think about organometallic reagents. Yeah, because organometallic reagents are strong bases as well, on the less subgroups. And we know that epoxide was here before. Now this one here is tricky. What do you guys think is going to happen between this organometallic or Grignard reagent and this carboxylic acid right here? Yeah.
Or you just deprotonate the carbon and then
Yeah.
protonate.
Correct. Right. This right here is acidic. This right here is electrophilic. But we know that the acid-base reaction is faster than the nucleophile electrophile reaction. So if it has a preference to be a base or a nucleophile, right? A base to attack this hydrogen or a nucleophile to attack this electrophile, it's gonna choose to be a base because it's a faster reaction. So the strong base here.
But I get you're gonna do one of them. You're gonna get two.
Would
One's gonna be like deriving all the different.
then we'll draw units on here. This is acidic, acidic. Deprotonate the carboxylic acid to get us this carboxylate ion and this. We also MGPR still goes away, but this carbon gained a hydrogen from this carboxylic acid right there.
Yeah.
Yeah.
What if you had like, let's say you had like a second, you had an alcohol on the fourth carbon, you had a carbonyl. Would the alcohol still be considered acidic?
Yeah, that would be the acidic one. The alcohol hydrogen is the acidic one. That's the question. Because let's say I have this right here, and then we have carbonyl here, and some like alcohol right here, right? We have a competition between the electrophilic carbonyl carbon and this acidic proton on the alcohol. Like you said, the base reaction, acid-base reaction is faster, so we're gonna deprotonate that to actually get to get this right here.
Still gonna cut it last year.
Right, where we deprotonate the acidic proton because this acid-base reaction is gonna happen faster.
And then I just because my immediate assumption was that it's not that acidic because alcohol, like if you were to deprotonate it, there's not a lot of resonance, so it's not that acidic.
Yeah, so this right here is a less stable conjugate base than
The carboxylic acid.
so the carboxylic acid one, right? But the oxygen here is still like the negative charge is on the electronegative atom oxygen, right? Which like is able to happen because this is a very strong base. If we use like another base like NaOH or ethoxide ion OR minus, we won't deprotonate that alcohol.
It's just because gradient's so strong.
Yeah, it's a very very strong base. Yeah. So you give it like NaH. Yeah.
Oh yeah.
Good crystals.
I heard that is a non-zero.
Well, I guess it doesn't make
So for this one right here, this one, I'm just going to show you the reaction here, but this one can work on methyl, we were talking about the primary, so 50 secondary, tertiary alcohols into right. So let's say for example, all this are SN2 reactions. We can do this. And then the product of it. And because it's SN2, we know that invert stereochem. And for SN2, do we form any carbocation intermediates in the mechanism at all? No. No carbocation intermediate, so we do not have to worry about rearrangements. We do not have to worry about hydrogen shifts or alkyl shifts. So, no carbocation
I just like loaded my calculator and I got the simple form and I was like, I could do it.
Now, I'm gonna create synthesis problems based on what we talked about so far. Epoxide opening, organometallic, redox, and these SN2 reactions right here. And some other ones as well, like halogenation, ring opening, Williamson ether synthesis as well. For you guys to try. Yeah, like all summarized into one.
Yeah,
one
it's like all
chart.
of chapter 8 just there.
Yeah. This one right here. Yeah, this is a halogenation. This is organometallic and a primary substrate. This organometallic is a strong electrophile. This is the electrophile. This is a good leaving group. This will attack this carbon and kick out the leaving group. That's an attack. There is no halogenation because we don't see X2 in light, like Br2 in light or Cl2 in light.
But since the NPR and the BR itself are all pushed out of the bones, and they're just floating on top.
Yeah, they will float away into ions like Mg plus and Br minus. They just float away. And because they're not organic, you don't have to drop them. Yeah.
What about the reaction mechanism of
Does Farhart give you guys
Yeah, so you know how you have this carbonyl as a
He doesn't believe in those.
You also have this acidic protein right here. But acid base reactions are faster
I
than
probably got one. I
nucleophile
think I just, well,
reactions.
let me not say this. I think I just.
Yeah, that's why I'm so scared for this class.
I thought you just said there's only I3.
Is there such a thing as like, I know that that's how you convert alcohols into halogens and then the PI3 you make in situ. Why is it always I5?
Oh, it could be I3. I'm not too sure with the last one. I just see PI5 sometimes, but it could be some other reagent as well for that.
Alright, so if I were to make it in situ, like what I just showed, like, so like just P, comma, I3 or I5.
Yeah, right. Let me go. Like, you guys still need a picture of this, or 'cause I'm gonna move on to synthesis files now. I'm just gonna do one big one that includes a lot, and then we will take a break.
Yeah, well, I was thinking, I have.
So let's say. Okay. Okay. So let's say we have this synthesis problem right here, where synthesis problems will give you a reactant molecule and a product molecule, and they're gonna ask you the steps to convert or transform this reactant molecule into this product molecule. And it could be 1 step, 2 step, 3 step, 4 step, 5 step, 6 steps, doesn't matter. You gotta figure out the reactions to convert this molecule into this molecule. And there could be more than one right answer. There could be multiple pathways to convert this into this. Some pathways will give you a higher yield of this, other pathways will give you lower yield of this. Right? So here's my step-by-step process on how I think about this. The first thing I do is I find the similarities between this reactant molecule and this product molecule. Right? So what similarities do you guys see in this reactant molecule and product molecule over here? Yeah. So if we number this 1, 2, 3, 4, and this isn't the official nomenclature. I'm just gonna say that 1, 2, 3, 4, 5 like that. Right? This isn't the official nomenclature. That 1, 2, 3, 4, 5 carbon here is gonna be 1, 2, 3, 4, 5 carbon right there. Where we see the new groups are gonna be this and this, like that. Okay. And the alcohol and carbon 2, like you said, is still there. So there are different strategies on how to do the synthesis problem here. The best strategy that I think is retrosynthesis, meaning when you go backwards, right? And then once you do that, I would go forward and then meet in the middle somehow and hope that it's the right process, okay? So let's look at this over here. We see a new carbon-carbon bond, right? And when you guys think of new carbon-carbon bonds, what reaction do you guys think of? Grignard reagent, right? Right? And then, you know how we have a Grignard reagent here, and we have an alcohol here. If we go backward, right? Like, let's say this was the nucleophile, which was the one attached to the MGBR, and this was the electrophile. And this right here was the new bond between them. What was this alcohol before? Like, if I go backward here.
Oh, that's not an OC.
I know that this right here is the star, the nucleophile, because that's the one directly attached to the MG, which is the star right here. But we're trying to go backward here. What was the intermediate before this right here? What did this alcohol come from? Carbonyl, carbon double bond oxygen, right? Which is going to be this right here. Right? Because we see that this carbonyl carbon is electrophilic, partial positive charge. When this nucleophile comes in to attack this carbonyl carbon, push the bond to the oxygen, it becomes an O minus, which will become protonated to become OH right there, to become the alcohol. And this is the new bond between the star and that carbon right there, like that. Okay. Any questions on how I went backward here? Right. So a lot of these right here, you have to have a really strong grasp of the reactions, like going forward and backward, and the relationship between the functional groups. Yeah.
I was just wondering, for the Grignards that you're at, do you have to add in diethyl or ether? Diethyl ether?
Oh, this one right here? So that diethyl ether is going to be the A product solvent, like that. Oh wait,
like, yeah, that's what I'm saying, because I know you add it for when you're making it, but what if you already have it? Do you still need it?
You don't need it anymore.
Oh,
right.
Okay.
If you add it there, it won't interfere with the reaction because it's very stable. It's just going to be there. Right. You can if you want to, but it won't affect the reaction. Yeah. Okay. Now, we see there's 1, 2, 3, 4, 5 structures. There's 1, 2, 3, 4, 5 structure right here. We see an OR group here and a carbonyl right here. Right. So let's say this is 1, 2, 3, 4, 5. We have this OR group and this carbonyl here. Okay. Now, what reaction do you guys know that has an OR group? And let's say this carbonyl was something else. Like, what reaction do you guys think of when you see an OR group and another oxygen adjacent to each other, right next to each other? Epoxide opening, right? But you know how when we open up epoxide, the epoxide becomes an alcohol? So we could say that this was an alcohol before. So we could go backwards again. Yeah. Alcohol. And what kind of alcohol is this? Primary, secondary, or tertiary? Secondary. So what kind of oxidizing agent do you want to use? Does it matter? No, it doesn't matter. You can use PCC or you can use Jones. It doesn't matter. Any kind of oxidizing agent would oxidize the secondary alcohol into this ketone. Okay. Now we see here that there's an alcohol here and an OR group there. What was the nucleophile? The alcohol or the OR? The OR. Now, if we compare these two carbons right here, what did it attack the more or less subcarbon? If it attacked the more subcarbon, did we already in acidic conditions or basic conditions? Acidic conditions, right? So we go back here, say that this was an epoxide, where this carbon here is a more acidic, more substitute position, where we're going to be in acidic conditions and have this ethanol be in acidic conditions there because we attacked the more subside. Now, this reaction we didn't go over, which is epoxidation. What do you think came before this epoxide? Like, what was in between these two carbons right here? Bromine could be here, right? But we want an alkene here, like a double bond here, right? Like this. Like, oh, I think you were thinking of intramolecular Lewis synthesis, right? Yeah. Oh yeah. So in this case right here, we want to do bromine instead because we have an alcohol right here. So that's the route we're gonna go to. Oh, okay. Right. Okay, I'm gonna show you guys different routes here, but let's say those was bromine right here. So let's say we have this OH and then bromine right here. What reagent would create this epoxide? NaH, right? Because what would the mechanism be like? What would the H minus do?
Yes, it takes the H, it turns it to H2.
It turns it to H2, creating alkoxide ion, O minus. O minus comes to this carbon, attack that carbon, pick out the good living group to form this epoxide right there. Right? Now, how can we put a bromine on the tertiary position here from this?
Radical halogen.
Yeah, with Br2 and light. Right, like that. So this right here would be the synthesis step reaction to incorporate this into this, where the first reaction is free radical halogenation, intramolecular Williams ethane synthesis, open up epoxy in acidic conditions, oxidation of secondary alcohol, and then organometallic reagent right there. Right. Now another thing here could be something like this. Have you guys learned about dehydration reactions of alcohols? Right. So if I put H2SO4 and heat, what do you guys think that's gonna do for this alcohol?
E1.
E1, right? Because H2SO4 would protonate the OH, we get into a good leaving group. I'll throw a sodium ion, make the leaving group leave, form a carbocation. Once you have the carbocation, you always stop, and you look for carbocation rearrangements like a hydride shift or delta shift. We could do a hydride shift there to get the tertiary carbocation. And then with heat, E1 is going to be phasing, where we make a double bond on the most substituted position like that. Right? And we can go from here to here using
MCPBA.
MCPBA. So you can also do this route as well if you want. So let's say the product looks something different, like this. There could be one more step here. Let's say we have that. What would be the last reaction to convert this into this?
Oh, you do PBr3.
So the difference here is OH got substituted with Br, right? So it's going to be one of those SN2 alcohol reactions with the weird reagents. And because we're using Br here, we're converting this tertiary alcohol into Br, we want to use PBr3. PBr3. Like that. PBr3.
For this one, it's already at a dictionary, so can we just use HBr?
Yeah, you can use HBr as well, right? In this case right here, you could use HBr, where the alcohol would get protonated by the HBr, turn into the good leaving group, pick up the good leaving group, tertiary carbocation. And then in this case, we don't have to worry about any shifts because it's at its most stable position. Br minus can come in attack and then get that right there. But I'm gonna put a star right here because
It's like weird.
right, and also it has carbocation, which like if this wasn't the most stable carbocation and there was a more stable position here, the Br would be at a more stable position there instead.
So should we just not use those?
For synthesis, I would use PBr3 all the time. If you see an alcohol to like Br, unless you see like this alcohol was at the less subposition and you see like on the product you see bromine at the more subposition, then you would have to use HBr for that synthesis problem.
Wait, when do you have to use HBr? Sorry.
Yeah, you would have to use HBr if, like, let's say this was a secondary alcohol, like ignore the isopropyl group, and then there was a like a trig butyl BR here, right? So something like this. And then we want to convert this into this right here. Right. This is when you would have to use HBr. Right. Because the mechanism.
Oh, because of the hydrogen shift.
Because of the hydrogen
yeah, okay.
shift.
Oh, I see.
But if you have something like this right here, let's say, you would have to use HBr3. Right? You cannot use HBr to convert this into this, right? Because of the hydration.
I was also wondering, like,
Yep.
at least for like when you said HBr could also work, don't you risk a chance to be one though?
Yeah, you could also do E1, which is the side product, which is why this is less favored.
Okay, yeah.
Right? And also, that just reminded me, you could cleave this ether as well.
Well, because it's so acidic, it turns it.
Yeah, it's super acidic. So actually, because if we have this ether right here, we don't want to use HBr because ether can be cleaved by HBr. If you use HBr, the ether can also be destroyed. Right? But if ether wasn't there, then you can use HBr. There.
I was making sure I added double.
Yeah.
Wait, the bromine would go on to the tertiary then if it were to cleave the ether, ether?
Yes.
Yeah,
yes.
okay.
Right. Because if you look at the
carbon
order
atom.
list, it's tertiary over methyl over primary over secondary for the ether reaction.
And then the H would go into the O, making an alcohol?
The H would go into the O, making an ethanol alcohol.
Okay,
Yeah.
okay.
Yeah.
Interesting.
Okay. Okay. So that would be it right there.